Hello everyone, welcome back. In this final part of this tutorial series showing you how to make the Helix Bridge in Singapore with Grasshopper, we will finish up where we started from the last video, which is building these uh, mini trusses, more or less. So, for example, this one here. Um, And then after that, maybe we can have a look into how we can sort of like build these balustrades that you see on the sides. And that should be the end of this tutorial. Like I mentioned in one of the videos, the mesh screens that you can see here and the glass screens, I will not be including that one into this tutorial series. Maybe that could be a sort of continuation or revisit for a future part two, perhaps almost, of this tutorial series, but we have to see how that will work out. But yes, so as I said, we'll be continuing making sure that this one will be included, will be handled, and then we can look into that one. Those are the two main topics that we'll tackle today, and as the last topic that we will tackle in this tutorial series. So with that said, let's clear our screen and let's minimize these and let's get on with it. So we finished off with all the sort of like medium thick rods, support rods, and let's disable this one so that we can turn a bit better. Piping is always a bit heavy. We can turn back that one so we can just see the lines. Oh, we don't need to see the lines yet. So, okay. So this is where we left off, and my strategy for trying to include all the interconnecting lines between inner and outer helix, um, it's going to be involving some Boolean operations. Because as you can see, if I can open the picture once again, maybe I should zoom in a bit, like that part. As you can see, this point doesn't necessarily mean it will connect to a certain pattern or a certain series until the next point. This one just happens to have one connection to the inner helix. This one has one, but this one has two. This one has one and has two and has two. So there's not really, or at least I couldn't find a certain pattern that dictates this behavior, this connecting behavior. Maybe there is, and I just needed more information. But I found another way that, as far as I can see, can also do all these connections without knowing if there's a pattern or not, because we're not going to be relying on that. If the architect has a pattern designed for this, then that's cool. But as far as I can tell, I don't see it. And I believe they've done the method that I probably will be trying also. So what I want to do is I'm going to connect well, first and foremost, I can see that these don't have connection because it's weird to have this one connecting all the way there, because I don't think that's needed, or actually this one. But anyway, so first we need to call off these, I think 1, 2, 5, and then we can start doing the real business. And what I'm gonna do is I'm gonna have one point, let's say, okay, I'm gonna be isolating this in terms of according to the planes that make up this line. So actually, no, I cannot show you that on both screen. But what I mean by that is I will have this one point, okay, connecting to whatever point it can find on the inner helix. So it will connect to here, and I believe there is another point here that's on the same plane. It will also connect there, and I think there's another point, so it will also connect there. So from this point on, those are the three possible connections that it can make. If I were to slice this in this frame, and the same goes for the one at the back. or this will go for, let's say, this one. It will connect there. It will also connect there, also here. So the same thing will repeat, and the more you get into the middle part, the more connection one point can have. And when those connections are made, what I want to do is I'm going to use the circles that we use for the inner helix to draw a big tube in that goes all along till the end, the whole tube here. And I'm gonna use have points on this line, on the curved lines. Like I will want to have one here, one there, one there. So each line will have 3 points basically. If this is a line, it will have a point here, here, and here. And how I determine this is I don't want it to be at the end because I want to be a slightly bit inside so that my Boolean operation can catch that. And always a point in the middle and always a point on the other end, also a bit shifted down inside. The goal of this approach is that I know, let me clear this. Because if I were to look at, let's say, if I were to look at this line, right? I already told you that it will connect 3 times. Actually, it won't connect. Okay, it will connect 2 times actually, because there's actually we won't be including the horizontal beam because that one's connected with this one instead. Or maybe it will, but we'll see. Anyway, what I want to say is, and then this will have 3 points. These 2 lines will have these points. And with that Boolean operation going on, I can be certain that this top line will not intersect with my Boolean. But this will. It's either going to intersect here or here. It will intersect at one point one way or the other. And that's exactly my way of eliminating this line and having the other line stay where they are. So with that theory explained to you, what I want to do is put this to the test and we can have a look at how well it works. As I said, I want to do the top half. There's no need to do the bottom half, and we can take that one. Yeah, I should take this whole bunch and just replace the top with the bottom. We don't need the horizontal beam, so we just continue closing that one out. Let's rename this just for clarity's sake. Otherwise, if you come back here one day and then you'll be like, why are there 2 with the same name that reference different elements? So with that said, now that we have these points, we need our planes. Where are they? They're here. Should I? I'm just gonna fork one off using a different component because this part is a bit special. Let's say these are their planes. As I've said, if I look at the top view, as I said, there is actually a number of sections where it skips before it starts. For example, in here, I think I counted 5. 1, 2, 3, 4, 5. So I want to get rid of the first 5 frames, both the start and the end, from here. So what I can do is just say, I want to call them away with index. And I want to have a number generated for me that starts 0, has 5 numbers. Where can I get a 5? Actually, 1, 2. It skips a whole section plus 1 if I look at this closely, because 1, 2, 3, 4. This is one section until that point, until this point. And the next point is where you can see the first branching off, or the first in between intersection. So what I'm going to do is take, I think it was this one, wasn't it? Yeah, this one. I'm going to copy that actually. Maybe I don't need to copy this, but I do need a panel. And I'm going to use it somewhere here, and I'm gonna say sections to modify for section to modify, just that, and that's one. Okay, and with that result, I'm just gonna plug it into a number. Well, actually, I don't need to do this, to be honest. Let's say, no, wait, let's do it simpler. Sections to skip. And let's just put this to 5 instead, and we can ignore all this nonsense. There we go. This one I can bring a bit for. I also need one more item, which is um, the total of items I have in here, which I can actually get from the plane. So that's a fine. So let's say list length is gonna be that, which will give me a number. It's gonna be 101. And what I'm gonna do with this number is, okay, let's create this one first. I'm creating a pattern for culling if you still don't know what I'm doing. This is the pattern that I can use to call the first 5, but I also want to call the other 5 on this end. So I am going to do a evaluation command. And but actually I can do it this way. Let's do 2 list items. I want 5 items. One of these can be counting downwards, starting from the total. There we go. And now if I were to merge these two together, I should have the pattern that I need, and I should have 10 items. There we go. And I can flatten this, actually flatten. This is the culling list that I will be using. So then I can actually move this into the eye, call my planes, hide all that. I don't need to see this. Okay, and now my planes are set. And now what I want to do is use the intersect with planes, curve and plane intersect, which I think is this one. Okay, so that's the amount of curve I have. So this will go into the intersect, and this will go to the planes. Actually, on second thought, because we need the points from the outer helix to connect to the inner helix, it might be easier for us if we don't merge them yet, but instead have them separated for now. And let's do them separately on this one. And we have some grafting to do here. Okay, so to back it up a little bit, what we want to do here is each of these planes, we want to organize the points according to the planes that they intersect. So it will be wiser for us to flatten the curve and graph the planes, so that the points that we will get is going to be first and foremost categorized by the planes themselves. So if I were to simplify this part, what you will see is I will have a maximum of, I think, 91 first level tree, a branch, as you can see on the first row there. And the second number on the second level of branch that you see is actually the number of helices that we have, 276. 276 items. So we can actually do the same now for the top one, or the outer helix. So this will go here. And in the end, what we want to do is, I think we might need to trim the tree a little bit in order to make it slightly more manageable. Because in the end, we want to have all points on the same plane, both the outer and the inner, to be cross-referenced with each other. And it will be easier if we just trim the train down back to the level, back to the amount, of planes that we have. So if we do this, you can see that we have one level with 92 branches. And now what we can do is open up cross-reference. Oh, not this one. Cross-reference, holistic operation in sets under sets list, and cross-reference this one. So what this will do, it will connect the list, the first list here, the first branch of points to all the other branches, all the other 92 branches of here. So what we're gonna get is, with that being done, we can have one point connect to all the other minor helix points in order to create our lines. So for example, if I look at A, let's see, this is A. It has 16 items, which means if you look at the first branch, we have 4 times the number of elements that we have on the first branch here, which is also 4, gives you 16. So if you look at 91, it'll be 3 times 3 should give you 9. There you go. The last branch has 9 items. And what we can do here is simply just create a line. Well, not this line. The line where you accept 2 points. Turn that off. So I can do this. And we get this. If you look on the sides, they're all constricted to their own planes. All the lines, all of it. And if we can zoom back into our first one. Okay, and now we are ready to do our Boolean operation that makes the whole thing appear, that does the whole magic basically. We want our Boolean geometry, not this. No, we want our circles, to be honest. We want that circle. So we're going to copy that. Actually, we might have it here, I think, right? Yeah, we do have it here. So we can just reuse this one. Okay, let's actually loft this in order to create the tube that we want. Remember that you have to get the tube that corresponds to the inner helix. With that said, we can, I think we can cap this into a solid. Now it's an open. Or actually, we can just do here, close lofts. Would it also work? Oh, that will not work because then it will, okay, I mean, that can work, but in our case it will, because we have no weird bridge. But I just prefer the capping. Then we're not modifying the geometry that we intend to have. So now that we have this geometry, we can pull that down ever so slightly to the level that we need it here. And actually I can drag all these down for a little bit of space. I can move this all the way here. And now I need to prepare these lines for Boolean operation. As I've explained, actually I want each line to be evaluated. So what I'm going to do is, should I flatten? Does it make sense? No, I don't have to flatten. What I want to do is, actually I think I do need to flatten because I want each of these curves to correspond to a CRV evaluation in order to create those 3 points that I mentioned that will have to exist on a curve in order for us to use, where is it actually? I think it's an intersection. Or was it a points? Here, wasn't it? Wait, what was it? Surface. It wasn't surface. Surface point in B rep. Since we only have one B rep, we can use this one instead. What does it matter if you use this one? What does this give me? Index. Okay, no, it doesn't really matter. We don't need the index since we only have one B rep. So the B rep goes there. The P are the point for inclusion that we're going to be using that comes out from here, and the strictness, I think we can just leave it as false as default. And now I'm going to make up the parameter for the curve. So let's start. We will have a center for sure, and maybe we can start with a 99, not at the end, and a 91, a 0.01. So with these parameters, we will have 3 points, one sits in the middle, one sits just at the start, and the other just at the end of each of these curves. So we might have to, because right now we have 4055 times 3. So that's obviously not working. So we need to graph this. So in order to make sure that every point, every line will have 3 points. That looks a lot better. 3 times 4, 12. Okay, with that being said, and then we can put, do I need to clean this tree up a bit? I might need to clean this up a bit. But we'll see. Okay, let's have a look at our results. True, false. So the idea here is, I think it is true if a point is inside the BRAD. So true if one of these points that we made here is inside of it. So we're looking for a line that has all false. If there's even one true, it means that it's gonna intersect. It's gonna be a line that we don't want, basically. So basically, these like line that has that's in this level, in this branch, will be a line that we need, that we want to keep, and all the rest will be false. So now that we have this data, how can we turn that into a usable in a usable form that we can actually utilize? If you remember, true is actually a number 1, and false is 0. So what we can do is, if we were to do a mass addition on all those numbers, if our theory is correct, then if the result turns 0, then that means that that line is not intersecting at all, because it will have 3 false value, and 3 zeros still equals 0. And now we can actually do in a evaluate command, and we can say, let's do this in here. We can say, if x is 0, then I want to keep it, else I don't want to keep it. Okay, plug that in here. This one can go to the x. What's the tree like here? 4054. That seems to represent all the lines here. Let's see. Well, we can graph this one, and then we will have it. Actually, let's flatten this. And we can also flatten that part. Now, I just hope that the order is not screwed up. We don't need that one. So we can say calling pattern on those, on these. So let's move down a bit, and that goes there. Here we go. Now these should be all the curves that we would want to keep, that are connecting from helix to helix, basically. So if we were to look at the, let's examine the first few here. So the first one, let me pull up a picture and see how well we're doing. So the first one is only 1, and the second is only 1. The third is connecting here, but also on the side, isn't it? 1, 2, 3. This is this one. So it's also connecting to the side. And then we have the ones that connects twice from the top, and then again to the side, and then 1 from the top, which is this one, and then another one that connects 3 times, or 2 times actually, that one. So it seems to me at least that our method works, which it should. And now we can give this, I think this one is a lot thinner than the rest, than that one, so that one obviously will have a different radius. So let's actually, oh, it's not that one, it's actually way over here. So actually let's connect this to the curve, but instead we're gonna divide this not by 5, let's say divide it by 8, and we're gonna give it a different color, obviously, maybe something like that, I don't know. Can disable that, can put those up in here with the rest, and we can turn that on. Okay, I've actually went ahead and enabled the other one also. Do be warned that if you've, like me, set this to render mode, it will take a while, and moving around would also be very sluggish. So if you want to still move around, look at your design before you finally render it out, probably a good idea to set it to shaded or wireframe for that matter, so they can navigate a little bit better. But this is how it looks like, actually, with everything in place, all the lines where they should be. See, it's very sluggish, so I'm gonna quickly go back to shaded, remove our plane, and then this moves a lot more quicker. Okay, one final thing we're just gonna be tackling, so we can actually, let's finally, we can rename this. Oh, I accidentally pasted it without shift. That doesn't matter. Just drag it here, and then we just call this support. No, wait. Secondary. No. What are these called? I think it's just called tension rods or not. I'll just call it support slash tension rods. Something that helps you identify. You can name it wherever you want. Okay. Let's give it a nice different color that we can sort of, well, why do I always have the same color selected? Just a different color, it doesn't matter which color. Anyway, so that's it for the rods. Next thing we're just gonna tackle for the glass balustrade. Okay, let's move on to the final part, which is going to be the glass balustrade. So we're done with that. To start off with the glass balustrade, obviously we need to, I think, build up from the deck, which is this one. We need an outline for this, so let's see. Maybe we can find it in here. Well, actually in one of these, because that's where they come from. I think this one. That's for the parts, which I think we can use later on. Well, okay, here's what we're gonna do. We are going to extract this one, and I'm gonna call this deck geometry. And we're gonna extract it in this way. You might want to build this from here on out, so let's do it here. What I want to do with this, I want to extract the outline of our bridge using a plane and B-rep intersection. We just call it a section. Coming from an architecture, you should be very familiar with this one if you're using Grasshopper anyway. So that one, wait, why is it giving that? Intersection failed. Oh, am I not intersecting anything? Oh yeah, that could be true. Wait, yeah. Okay, so let's define the plane first. Let's deconstruct the B-wrap, and that's the B-wrap we want to deconstruct, so that we can get a point in order to make our outline. Well, the point that we need is obviously the one with the highest point, the highest value in the z direction. So what we can do is let's deconstruct points using that one, and then we can sort all our points according to their values. So the one we want to select is obviously the top one. So we can attach one here. We reverse it so that we can have the top one, and that's going to be our plane. And that is also our intersection. Well, as you can hear, it actually cuts it off at here, which is not really a problem, because then what we can do is just region join this actually. So we can do region union and flatten that. I think we need this one here. Is it giving me? I don't think it's giving me that actually. I think we need to get rid of that. Or actually, one easy way to do this is to move our plane down by a little bit, and we can, so that we can use it to cut it in the middle, which is more reliable. So we can say, let's say 0.1. It's a small number. Do we need to have it move downwards? Minus x. That way, we'll only have one curve. And then we just move it back up to the position where it should be. And there we have it. Because we were, the reason why we had 5 is because it was cutting just at the edge, just as the top, and the top for us event contained that this line here, and it actually cut that line in also. That's why we got the results with 4 curves instead of 1, which is the one we expect. So we can actually just use this one. This is only a little trick, but it helps. You don't need to do much with it. It will always work. Let's focus on the main rail first and not look at the viewing part. So what we can do is let's actually let's explode it using discontinuity, because we know this is a hard joint. It's not smooth, and we can shatter this using the same joint where it created. And what we can do with this, we can filter out. So we can just say evaluation command, and in this evaluation it says if we filter by length, so we can get the viewing part out of our filter list. So we can plug that in, perhaps maybe there, and we're gonna use a call index or a call pattern to call away the ones that we don't need. Our formula is going to be 10. Let's set up a slider that has 10 and maybe 50, 10 to 50 meters. So we can say if x is smaller than y, then call it, otherwise keep it. Something like that. But actually we don't really, let's use a dispatch instead, because we need to use the other ones anyway. So instead of deleting it, we just use the dispatch. And to make sure that we actually have the ones that we want to select, let's filter this out. So we only have this. We need to move until it also incorporates that part. Oh, I see only one thing also. We don't need the ends, to be honest. Well, we'll see what we can do with it. So I'd say about 35 meters, is it? Or 30 meters. It will include also our viewing parts. So let's say cut off threshold, something like this. Okay, now that we have the curves that we want to modify separated, we can focus on, let's focus on the top one first. We should have 1, 2, 3, 4, 5, 6 curves. Yes, exactly. And we're gonna split them in the same way we split all our curves, our helices, which is using the frames that we use all the way in the beginning also, which is these. I wonder if I can just copy it from somewhere. No, you know what? Just no worries. We just do it again like this. We might even need the bridge section anyway, so that's fine. Let's copy and paste it here. This one will obviously go there. Oh, we do need the main curve. We forgot the main curve. Like that. Okay. And we want to use intersect curve. Let's just find it here. It's a lot easier. That one. These are the planes and these are the curves. Oh, we do want to have, let's do this one. We do want to have, let's see, which one will take precedence. We do want to have all the planes intersect with all the curves, so we can just graph this one. There we go. I just found one thing. Maybe we should do something else first, and that is because right now we are actually saying, hey, I want this I want the glass to start right at the edge of um, a deck. But if I look at this picture, there is actually sort of like a slight um, inset, sorry, slight edge to it. So what we can do is right off, I think here is where we can apply an offset. Offset curve, this one. Well, not to the outside, but rather to the inside. So we're gonna do the expression to minus x, and we're gonna say, I don't know. Let's say 0.5. Oh, oh wait, 0.5 is a lot. 0.05. How much is that? 50 centimeters. That's a lot too. Well, if you look at it, it seems okay. Okay, we can actually go a bit lower. Let's say 3. Offset to inside. Or offset for edges. Or offset at edges. Whatever is easy for you to remember. But anyway, so we're going to do that. We're going to replace this here. And now, we should have a point that's slightly more offset inside. We can see it a lot better here. You know what? Just on second thought, let's just go with this one. We can always change that later, so it doesn't really matter to us. Okay, now that we have that, let's start creating the poles first, actually, because we already have this. What we want to do is we want to identify the vectors, where we're going to be placing a center box, which will represent our balustrade poles. These. You can make it as nice as you want, but once you've got the base principle down, it should be easy for you to change it to whatever form you want, replace it perhaps whatever form you want. So that will be fun. Okay, so with that, let's do, in order to get the vector, we can use curved closest points. Now I don't know where they are. Wait, what? Curve point. This one. Let's have a look at the data structure that we've created for ourselves. We have. Oh, don't use simplify for now. How is our data represented? They are represented based on the number. So the first number is going to be our planes. The other one is going to be our curve. Actually, let's flip this around. Let's say we want to have each of these curves, something like that. You want to have each of these curves be intersecting with all the planes so that we can have a nice structure where if we to trim the tree deck back down, this one, or we can actually use this. Let me see if I can use this. Let's see how that looks like. To be no, we cannot use that, or maybe can, but I don't want to use that because I'm not really familiar with that part yet. So once we trimmed it, we've got now 6 branches with each of their own trees. So we can actually use this one instead. Do we? Well, actually I can. If we do a CLV evaluation, we can actually say, I want that curve, of course, grafted, because the data that comes in here are grafted. We can actually, actually delete the one that we actually want. And I can vector display this first and see what I am getting. Okay. And if I were to rotate the vector using that one, this one goes in here. I want to rotate these obviously at the z-axis. So I can plug in there, internalize it, keep the data, right click, change it to degrees, and I might change this to -7 negative, but it looks like we have the right sections. Okay, so that's fine. What I want to do with this is actually create a plane that we can use in order for our center box. So we can construct planes. The origin is obviously the points themselves. Yeah, accidentally did that. The origin is the point themselves. The x-axis. Can I create a plane with a normal? Oh no, wait. I can actually I can do it like this. This one goes there. This one goes here. Because otherwise it will. Actually, I don't need that. Wait, let me turn the previous size of my plane back down to 1. I actually want this to be like this so that it can it follows the plane instead of following. Well, doesn't matter which one it follows, it will still be the same, except that now my planes. Interesting. It turns out I don't actually need to rotate my vectors because as I can actually just use that one on one of the x-y axis and it will follow it just fine. So let's delete that then. Now what I can do is plug this into a center box, create a domain, let's construct let's construct a domain that would define the dimensions of our box. Yeah, we can use both for the x and y. We can say let's do this 0.01 less than 3. Plug that one in here. Give it a small size to begin with. Let's go all the way to the beginning so that we can have a better look at how these things look like. For the height, let's give it a very large height first so we can see this is our actually I can do this that way. Oh wait, I need to control it using this, but how does it actually work if I just plug in this here? Would it go only one size? So that actually works too. We don't need this. We can use this one for the height or not. Well, we'll see. I think I should get rid of that. This could be a little bit bigger, I think. You might have to move the offset down even more. Let's say 0. Okay, let's do it 0.1. Then move all the way there, and this is going to be our pole. It's going to be like that. Let's see how it looks. Well, obviously not 5 meters, but rather more like 1 or even less. Yeah, I think this is 2 meters now because it expands in both directions. We can have a quick measurement of that in here. So if we were to do dim align in Rhino, we can actually quickly measure. What's that? That's 1. Yeah, so it goes 1 meters on both sides, and we don't want that. One thing we can do about that is actually create the domain that we deleted. Not sure if it will move like that though. Nope, apparently it will not. So let's create a more reasonable height. 7 to about 1.2. And this will be the height of that. And one thing we can do is minimize this by divide this by 2, x divided by 2, and then move it back up in the z direction by the amount we divided it by, which is the half of it. So we can do this x times 2. Wait, x times 2? No, x divided by 2. That's it. Got a little bit confused there. So this determines now the height of balustrade, something like that. And we can put this to 1 just to start. And now we have all the balustrade there. And the next thing we're going to tackle is the glass itself. And we can actually use, let's say this one. I should use this one. We're going to use the one that we filter out, which is going to be A. Starting from there. How we're going to do that is, nope, not this one. If I were to just quickly expand this out here, so we can select this and have this only show. What we can do, we can actually offset it like that, like offset the curve from here with 2 distances. We can actually, wait, let's use a panel to visualize this for now. Let's say 5. Can we do 5? 5 will end up there. So we can actually do is do maybe like 4 on both sides. So we will be doing a number. Let's go that in here. And then we're going to do also a negate, a negative, which will also go in here. And combined, we should have 2 numbers if we graph this. Actually, we should graph that one and not this one, because then we'll have 3 branches that matches what we want to do with the data. Let's trim this tree back down by 1 level, and we should have 6 branches with all that inside. In here, we might wanna do x divided by 2. So our glass is now basically 5 thick. It's actually quite a lot. Let's do 4. How would that look like? Something like that. Now, what we want to do is we can do boundary surface on it, but only after it's a closed surface, right? Because right now it's actually not closed, so we can use the component connect curves, and this will close the curves automatically for us if we use position. Or apparently it doesn't because the curve is flipped. Oh, well, that's not. Oh, actually, you know what? We can use loft. Why not? Although the loft is also not my favorite command, so to see. Okay, fine. We'll do it one way. We'll do it like this. We'll do connect, and we'll do position, obviously. But we are going to invert or flip one of these curves. It doesn't matter which one we flip. We just need to flip one of them. So if this one were to go there, this one were to go here. You may merge them before, but since I know we're not be changing a lot in terms of data structure, it will still match. So this will be our curve. We can have a look at here also. Actually, let's turn off all these so that we can have a better look at what we're doing. There we go. So now I can do boundary surface on this and extrude this in the z-axis with the same height of balustrade perhaps. And there we go. There's a glass. Well, sort of. Let's give it a material, or actually give it a color. So we can actually use this one here. This will be connected to that one. And let's enable this one. Let's disable that one. Let's give it a nice transparent-ish kind of glass. Like that. That's our glass for that, and that is also our balustrade, which let's give that also a color. It won't be transparent though, that'll be weird. It'll be something like slightly grayish. Something this range perhaps? Yeah, something like that works. Okay, and now we can focus on the parts, which starts from the other one. So we can actually move those. Take that. We're going to move it up a little bit. This one move a little bit. This one will be down. This is going to be focused on. What I want to do here is I actually want to get rid of the start and the finish. We will use our main curve endpoints here to say whichever curve is closest to these 2 points is the ones that we don't need, right? So with that logic set, I'm gonna do is do a CLV evaluation. We're gonna evaluate point with points. We parameterize this. We're gonna say I want just the middle point. Actually, let's skip that first. I want this to be the end results, as in the ones that we will ultimately need. So let's do point closest, I think, is the one we want. Point closest point. Okay. We want to measure from these points, and the cloud of point to measure to look for is these. And what I'm interested in is the index, because what I can do with an index, I can just say call from these index. And those are going to be our curve. And there we go. We've eliminated our start and end, just like that. And now we can actually begin working on this one. What I envision to do is I'm going to be doing the same as for the rest, but seeing as there's a pole here, I probably don't need that one. So we'll have to see how we're going to call that. We're going to have one here, we're going to have one here, one there, and these will be divided in a way that we can adjust ourselves. Anyway, So let's start. We have these. We might let's do it this way. Let's divide our curve based on the length, not based on a number, based on a length. And the length that we want to divide is the section width. Oh, so we can actually just take that here. Oh, I'm gonna take that here. This is the length I want you to divide. And what I want to do with this is, you can see that in this part, we have 2 points. What I want to do there is, why is this so? This tree structure is really doesn't have to be okay. So we are now having these. That's fine. Let's see. Okay, what I want is a list length, because apparently the 2.8 won't fit in there. So we want to say I want the list length of these. Should I graph this? Guess I can. What will I get here? Same thing, which is okay. I can apply it there. What I essentially did is, how much of 2.8 can you fit in there? Oh, you can fit 1 part, okay, which gives me 2 points. And then I want to use those 2 points as a number to divide it by segments, which then give me this process. And now that we have our points, we can actually go in there and use the same method that we used somewhere. Where is it? Where the box we created here. There. And there we actually used a curve evaluation in order to get the right starting plane. So I'm going to do the same here. We're going to do, actually we have it here already. So perhaps I can just do it in this way, which obviously works, except that for that part we might have to eliminate one of these frames, and for this we already have a plane, so we also will have to eliminate that one also, that part also. This one actually is something that is also universal, so that's for creating the glass, so we might be able to focus that later on. But what I want to do here is, let's evaluate this by length first in order to separate these shorter sections. Are these the ones? And let's sort these by length. Sort them in this way. And I might even move all these down and have all of these come from this line. And then that would mean that I don't need to graph that part, to be honest. Or I only need to graph this one. Or just graph this one instead. There we go. The reason why I did that is so that I can easily see how many of these should I partition out. Because I want to do a partition list in this way. Let's see. I know the 4 comes from the amount of viewing paths that we have, but is there a way for me to get that number somewhere from here? don't think I can. Well, somewhere around here, I say I need 4 viewing pods. Just not sure where anymore. But it was here. But apparently it's not. And okay, that shouldn't matter too much. Deck geometry, section geometry. Well, I know where I can find the 4, which is from the from this, the Boolean geometry. So I'm just gonna copy that and do a list length, list list length from this. Let's turn that back on. Let's say flatten that part all the way up here because I need this all the way here. And my list length is also going to take in the amount of items that I actually have. So I have a 12 and a 4, and what I want to do with this is, let's see, let's do an evaluate. No, actually, I can just do a subtraction. Subtract the 12 with the 4, I get the 8. And then I can use an entwine because I don't want to mess up the order of the list that I want to partition. The 8 actually goes in here. Actually, if I have 8, I will only get 2 numbers. I won't have more than that, to be honest. So this separates the short edges with the long edges. Actually, I don't need this one also. Just need them to be able to do that. And now that I have these separated, I can essentially do an explode tree that comes from this. Well, I don't need them to be that far ahead, so I can have everything go from here. Oh, one like that. Well, obviously this one will be applying to this. Obviously this one will only be needing the center value. So I actually should be doing this here. And I do need this up here. So I'm just gonna, where does this come? This comes from that. This goes to that. This also goes to here. And I only need the center one, which is integer number 1. Or, well, in our case, I know for sure that the that there won't be more than that. But what if you have more? That's an issue that we cannot solve with this. If you have more, what we want to do is we want to call the first one and then call the other one in reverse. So let's say call index. You want to call index 0. Can we do it here, or can we do it? I think I should do it here. So we want to call this, and at the same time, we also want to, okay, I have a better idea. Let's just do list length instead. This is the official way that I used to do this. I want a number, the total number, and I also want a number 0 in here. What you can do with this, you can actually merge let's merge these instead. Here the numbering order is not important, so I don't need to use an entwine. So now I have a 0 and a 3. If I flatten this, get this one off. Oh, I actually just need one item. I don't need all of it. So I'm gonna put a list item here. So I have a 0 and 1, and what I can do with this, I can use it to in the calling indices for this, and I can reuse that, and I can do the same for our vector. which should give us this. Two items. Two items. Well, this is an issue. Why are we calling with two indices and we still end up with two items, even though there are three items in the list too? Oh, of course. Index number 3 doesn't exist. It starts with 0. So I think I have to. I cannot do that. I can do it here also. I can just say x minus 1, which will give us 2, which will eliminate. Which we don't have 0 and 2 because we want to keep 1. So we're gonna keep we want to call the first and the last. So that will always be in our case 0 and 2. So it have more. If this were longer, let's say the neck of your viewing part. Let's see this part here. You will probably get more numbers than 3. And this method ensures that always the first and the last will be called, and whatever in between you will keep it. And with that part set up, we can move on to the next part of our script. Is I think we can actually reuse this. We can reuse that for sure. And we might be able to just merge these two together and apply it at once, like that. What are we missing? Oh yeah, it needs to move up. Or we can actually merge that plane with this together, but we'll just keep it separated for now because it's a lot clearer for us. Okay, if you add this there, let's flatten this part. And we have all that, and now we just need to figure out how to do our glass in this example. So let's move this a slightly bit up, and we can use maybe this one. This one we use it on our curve, which in our case is going to be the curve before all the culling, or after, right after the culling of the start and the end. So this is going to be our curve. Put it down, put it up, doesn't matter. Keep it here. And then what do? We also trim the tree back down in order to give ourselves a nice 2-2 pair. Aha, this is also, we then had to flip one of the curve of the pair because of the way the connect would then not work on that curve. So now that we have that, what's this? This is a extrude. Okay, I can put this extrude here, and also this can go up to the glass, and we can flatten that, and this is our end results. Put the glass a bit here, but you can fix that later by using. You can actually fix that by using the offset in order to make that work, or you can actually rebuild this whole part using a different offset, which is also doable because it's just one number here. You just need to modify this and change it into a number. Actually, not this one. The modify section that we use to modify the edges. So you can make that as perfect as possible, or you can actually not call away the first point. For example, if you remove this one, let's say if you remove that, you will get your beam back, and you just remove the beam that's on the long curve, which can also work, but I'll leave that up to you how you want to attack that. So this is our results, and if I switch to rendered briefly, it might take a while for it to render fully. Actually, might be a good idea to just first go into like that, and then turn on the rendering process. There we go. With that, this is the last part of the tutorial for making the Helix Bridge in Grasshopper. I hope you've learned a lot. I hope you've able to follow me until this point. If you are, congratulations. this has been quite a long journey. I think it spans about 2 weeks to if you follow this non-stop. For me, this project actually took more than a month to first set up the base scripts, make it all the way to the end, then run a second through to make sure I've optimized as much as I can so that you can have the optimized version and not listening to, well, a lot of trial and error. If I were to include that, this tutorial series would have been a lot longer. And yeah, so I hope you've learned a lot. I've had pleasure making this video, this tutorial series. I will continue to do so with other projects. I hope you will stick around, and good luck, and I will see you in the next video. Thank you very much.